Okay, let's consider the first question in your coordination compounds. Which one of the following cannot act as a chelating ligand? Chelating ligand means usually a bidentate ligand which can form a 5-membered ring or 6-membered rings are usually stable. So this ethylene diamine, when your ethylene diamine bounded to a central metal atom, what happens? There forms a 5-membered ring so that it is stable. So this can form a good chelating complex. What about this one? This may be bidentate, but the ring formed by that particular hydrazine is not much stable. Okay, but there is no chelation actually. This is less stable. Ready. So this can't act as a chelating ligand. Okay, it may be a bidentate ligand, but it cannot act as a chelating ligand. Here also, the ethylene group which is locked between two nitrogen. Okay, so its complex is something like a group is here. Ready, will be like this. Okay, so free cyclic ring that can form if the cyclic ring is 5-membered, then it will be saturated. If it is saturated, then it will be more stable. That is the concept. Okay, so free cyclic 5-membered ring which is actually formed only in ethylene diamine. So we can choose your ethylene diamine can form the chelate complex. Okay, so hydrogen and this one also not able to show the chelate complex. So the choice will be D. Okay. Next question. Consider the next question. Which of the following statements are correct? In the complex, CONH3 4 times CO3Br. CO3 2 minus is a bidentate ligand. Let's check the case. Okay. Here the charge is -1. So this is +1, -2, 0, +3. Since the cobalt is +3, listen, cobalt is +3. And the coordination number of cobalt in cobalt +3, usually the coordination number of cobalt is 6. Okay, no doubt. So here it is 4 monodentate ligand. So this have to offer a density of 2. Then only the coordination number becomes 6. Okay. So it is clear that CO3 2 minus is a bidentate ligand. Okay. What about the next one? The next one, here actually the coordination number of amines is 5. So your CO3 have to offer one coordinate one. So CO3 2 minus which act as a monodentate ligand. So we all know that there are different types of ligands which can act as monodentate as well as bidentate, and that depends on time. And that is said to be fluoxedentate ligand, right? The next is in nickel DMG twice. In nickel DMG twice, CO3 2 minus is monodentate ligand. I'm sorry, nickel DMG twice, 4 ring complex are formed. 4 rings are formed totally. So let's consider the dimethyl glyoxime structure. Dimethyl glyoxime means dimethyl glycimato. Okay, dimethyl glycimato. What the structure is? This is dimethyl glyoxal and glycimato, you know, this become a single bonded OH, right? Well, these two are the donor atoms. Okay, so consider the coordinate bond formed by this. This is actually single bond, okay? Fine. like that. The next one, is something like this. It's not O minus. This is OH actually, right? This molecule is OH, but the donation is from oxygen. The next one, double bond, or double bond C, followed by C, where this C have a CH3. This also have CH3, and OH is this is coordinated to here. Ready? Okay. Actually, there are two different types of complex are formed. But once the complex is formed, there is a chance for intramolecular hydrogen bonding between OH, H of hydroxyl oxygen and carbonyl oxygen. So there actually forms 1, 2, 3. This is 1, 2, 3, 4, 5. 1, 2, 3, 4. So 4-membered ring. Ready? So there are actually 4 different rings are formed means that's also correct. So the all statements are correct here. Okay. All statements are correct. Next. MnCO 6 times, VCO 6 times are respectively. Let's consider the valence electron of MnCO 6 times. Manganese is in 0 state, right? So 4s2 3d5 the valence electron of manganese. And carbonyl 2 into 6. So actually 7 plus 12. 19 electrons are there in the valence shell of MnCO 6 times. What about VCO 6 times? Vanadium actually 4s2 3d3. And carbonyl group have a valence electron 12. So 5 plus 12, 17. So 17 electrons are there, right? 17 electrons are there in VCO system. So if it have 18 electron, which means if it absorbs 1 electron, it becomes stable. So it have a ready tendency to accept 1 electron reduction. So this will be an oxidizing ion. And this have to become 18 electron when this loses that electron. So this have a tendency for reduction, oxidation. So this act as reducing. So first one act as reducing and second one act as oxidizing ion. That is the actual one. Okay, choice C. Ready? The next question, that is hapticity of this complex. Here the molybdenum, which is in pi interaction with the ring, but the ring where these all atoms have, these all are having a cyclic conjugation, and this jumps to here, this to here, ready, and this to here. Okay, fine. But this is an sp3 carbon, so there is no actual full cyclic conjugation. So what is hapticity? That is a number of carbon atoms which are in pi interaction with the central metal. So actually there are only 6 carbon atoms which are pi interaction with metal. This is actually out of the plane. This is an sp3 carbon. Okay. So actually 6 will be the answer, not 7. Clear? Next question. Only cisplatin react with oxalic acid forms PTOX twice, and not the trans isomer, because listen, when the cisplatin react with the oxalic acid, oxalato replaced, and this is only in the case of cis. They mentioned like this is only in the case of cis and not in trans. That's the right point, because a bidentate ligand can form a coordinate bond if they are in relative 90-degree position, which means cis position. Okay, they can't form a coordinate bond if they are in a trans position. Okay, but the bond is less stable. Ready? So they can't form a bond like this. A bidentate ligand can't form or can't exist as or can't chelate to the central atom by means of trans pattern. So there is no replacement of NS3 when oxalic acid is added to this complex. If that is a trans isomer, that's the correct, because if NS3 replaced by OX, it can exist in a stable pattern, and that is only stable in cis form, not in trans form. Okay, so that statement is correct. Oxalate ion is fine. This is a phenomenon, right? This is a phenomenon, and what you're asked to find means the explanation. Oxalate ion is monodendric ligand. No, oxalate ion is always didendric ligand. Oxalate ion is unsymmetric bidendric ligand. No, oxalate ion is a symmetric bidendric ligand. That's these two are not the reason. The third one, what about the third one? Oxalate ion is bidendric ligand and occupy the adjacent position only. That's correct. It can't exist in the alternate opposing position. It can exist in the adjacent position only. Ready? The next, which of the following is or are correct? After splitting octahedral field, Hund's rule is not violated. That's correct. After splitting octahedral field, we always follows the Hund's rule, right? We always follows the Hund's rule. So not violated means that's correct. NO is a 3-electron donor. NO is a 3-electron donor. That's also correct, because nitric oxide, the structure is something like this. Okay, so it can ligate through this over. So this is a 3-electron donor. That's also correct. Dithioxylate. What is actually oxalate? This is actually oxalate, right? Dithioxylate is bidentate ambidentate ligand. This is oxalate. Then what will be dithioxylate? Will be like this. So this is a bidentate ambidentate ligand, means either it can form a coordinate bond using either the donor atom, this one, or the donor atom may be sulfur. So it can ligate the central atom through different ends, and moreover it can form a bidentate complex. Okay, so that's the correct one. Ready? The next, MABED or MABCD, tetrahedral geometry. In tetrahedral geometry, there is no geometrical isomerism, and MABCD can form what? Optical isomers. That means MABCD can form optical isomers. Which are the following isomerism observed means only optical. Next question is that the magnetic moment of octahedral complex is minus 0.8, surrounded by a weak ligand. Fine. So this is a CFSE and ligand is weak one. Then what about the unpaired electron? We know the equation for CFSE. Minus 0.4 into number of T2G electron plus 0.6 into number of EG electron. This equation, right? Fine. So what configurations is satisfied to bring the answer as minus 0.8 delta? I think if this is 2, this is 0, that's perfect. Okay. So T2G 0, T2G to EG0 is okay. Then you obtain the minus 0.8. Now minus 2.4. What about this one? T2G3 EG2 minus, sorry, T2G5 EG2. T2G5 means minus 2.6 actually, right? No. Wait. If this is minus 2.4 and this is minus 1.8, then you obtain minus. No, that's wrong. That's wrong. If listen, if this is minus 2.4 minus 2, if this is minus 2 and this is 1.2, that's perfect. Okay, that's combination though. For this become minus 2, there will be 5 electron, right? So T2G5 and Pg2. This also can form minus 7. So let assign this configuration in a weak ligand. Weak ligand means 1, 2. Fine. This in weak ligand. 1, 2, 3. 4. Oh, in presence of weak ligand, sorry. In presence of weak ligand, 4, 5, 6, 7. Fine. P2G5, EG2. Right. So unpaired electrons are actually 3. So the chance for unpaired electron is N is 3. The chance for unpaired electron N is 2. There are two possible ways where we can bring the answer into minus 0.8 delta O, and which is in presence of weak ligand means the chance for the unpaired electron will be N equal 2 or N equal 4, N equal 3. If N equal to 3, what is 2 into 2 plus 2? Root 8 will be the get. So this may be the answer. And both A and B there is a choice. So let's check the B also, A also. If N is 3, root of 3 into 3 plus 2. Okay, that's fine, root 50. So both are possible. Okay, so choice is D. Clear. Next question. Which of the following complex can show optical isomers? MA4B2, it is not able to show the optical isomerism. MA3B3 also not able to show the optical isomerism. MA4BC, sorry, this is also can't show the optical isomerism. Okay. And actually the optical isomerism arises when MA2BCD from MA2BCD. Okay. So the choice is 4, I think. Next question. Which of the following compound shows ionization isomers? To form the ionization isomerism, your counter ion can act as a potential ligand. Here the all ligands are neutral, so it can't act as a counter ion, so this is not able to show the ionization isomerism. Here all ions are neutral, so it can't exchange as a counter ion. Here there is a anionic ligand, it can exchange with SO4, so this can show ionization isomers. Okay, consider the 11th question. Which of the following is D2sp3 hybridized? D2sp3 hybridized. So let's consider the whole where fluorine minus 6, nickel in plus 4. Iridium, all charge minus 3, fluorine minus 6, iridium in plus 3. Cobalt directly 0 for aqua, cobalt directly plus 3. So nickel in plus 4. Nickel plus 4. Normal nickel is 4s2 3d7. So when it is in plus 4, it becomes 4s2 3d8 is normal nickel. So when it is plus 4, it becomes 3d6. And normally, our expectation is 3d6 is like this. Okay. But we are considering the crystal field theory also. F minus is a weak ligand. That's perfect. But since the central metal have greater ionic charge, since the central metal have greater ionic charge, what happens? Greater will be the repulsion. Greater will be the delta O. Delta O will be greater. Okay. If nickel is in +2 oxygen state, no problem. Since this is in a +4 oxygen state, delta O will be more. So pairing will be favorable. Pairing takes place. So that D6 actually that D6 will be, even if it is a weak ligand, there will be a pairing since the nickel which is in +4. So actually there are 2 d orbitals are vacant, which means the pairing like this. So these 2 d orbitals are vacant, which can provide the D8 to sp3 hybridization. D2sp3 hybridization. Okay. So this is fine, D2sp3. What about iridium 3 plus, cobalt 3 plus? Actually, cobalt, iridium, they all are in same group. Okay. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt. Lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium. So all are in same. These two are in same group. But the cobalt, normal cobalt having a configuration of 3d7, 4s to 3d7. Like that, your iridium have 6s to 5d7. So in these two cases, they drop 3 electron. So become 66 here. This is a heavy transition metal. It always pair the ligand, always pair the electron. Okay. Whatever be the ligand, whether the ligand strong or weak, it can always pair since it is a strong ligand. I'm sorry, heavy metal. Ready? So this can also form D2sp. And there is a case when the cobalt is +3, cobalt which is in +3, and in presence of aqua and amine ligands, where these two behaves like strong ligand, where the hybridization will be D2sp3. That's an exception that you have to know. Okay, in presence of cobalt. So I think the all have same hybridization at D2sp3. Clear? Okay. So keep that question in your mind. That's a good question. The next is a compound made up of mixing cobalt 3 nitrate and potassium nitrate. Cobalt 3 nitrate and potassium nitrate. Okay. In the ratio of 1:3. Okay. 1:3. Cobalt 3 nitrate. CONO3 thrice. And KNO3. Which is in the ratio of 1:3. The aqueous solution of the compound showed 4 particles per mole. So this when these two stable compounds are combined, there may be formed a molecular compound, whether it is a double salt or coordination compound, whatever it may be. Fine. Now they said that in aqueous solution there will be 4 particles, right? 4 particles are there. 4 and the 4 particles are there. Fine. Where the molar conductivity reveals as 6 electric charges also. 6 electric charges. Sum of positive, negative charges is equal to 6 electric charges. So, what will be the formula? What about here? Potassium +3. This is -3. So this have 6 electric charge. That's correct. And when this ionized become 3K plus 1 entity. Fine, perfect. So this can also provide what? 4 ions. 4 ions, 6 electric charges. The choice will be C. Okay. Next question. They're asked to match the box, right? Tetrahedral, no doubt, NiCl. Octahedral, that is with the coordination number 6. Always coordination number 6 is octahedral. Square planar, we know that a typical structure for CuNH for 4 times. Linear for silver, trigonal bipyramidal, I think. That's for a quiz. Okay. So you can match that. 1 with the E. Okay. Choice will be A, I think. Ready? That's a simple question. Which of the following complex is expected to have optical isomerism? This is MA3B3. This can't show the optical isomerism. This is MAAB2C2. This is MAA thrice. This is MAA twice B2. This can show optical isomerism. This can show optical isomerism. This can show, but this is not able to show. Okay, ready. Here the cis form can show optical isomerism, right? Yes. The choice is 1A. The next is, which of the following complexes are strongest reducing agent? So find the electron of entity. Cobalt, now the cobalt, find the EN. Then we can predict the reducing character. Cobalt, which is in +2, I think, yes. Cobalt +2, forest 3D sign will be there. And 2 into 6 from the cyanide. So that's equal to 19. Fine. Next, cobalt +3. Cobalt +3 means 3d6. 3d6 plus 2 into 6. That's equal to 18. Silver. Silver with atomic number. Silver is actually AgCN2 minus will be the case. Okay. Ag plus. Fine. What about the configuration of Ag plus? For the valence electron of Ag. Ag half valence electron 3d10. 2 into 2. 2 into 2. 14 electrons are there. Okay. Cu is +1 here. So this also 3d10, right? This is actually 4010 anyway, d10. Plus 2 into 4. So this is 18. So as per EN rule, now simply I find the valence electron. These valence electrons are stable. And these have a tendency to increase the electron. So act as, which means it wanna reduce, it want to gain the, this want to gain the electron. So reduction, oxidizing in. But this cobalt complex have to lose that electron. If it have to lose that electron means what happened? It will be a strong reducing. Choice will be A. Okay. The next question that is consider the following reaction. M GLY EN4 plus. Okay. So ethylene diamine is replaced by GLY and become MGLY twice 0. Okay. If reactant has no stereoisomer, okay, but exists into stereoisomeric form. If the reactant have no stereoisomer, fine. The reactant is actually a square planar complex, I think. That's why it do not have a stereoisomer. This is a category. This category have no stereoisomer. That's perfect. Because we have two possibilities. If this is in tetrahedral, we want to expect the optical isomerism. But we discussed that if there is a symmetric bidentate ligand, then there will be a planar symmetry. There will be a planar symmetry in this plane. So no optical isomerism. If this is a square planar complex, then we have to consider the geometrical isomerism. This is not able to show the geometrical isomerism because always here is AA. So we can't predict the system lines. So that's correct. If reactant has no stereoisomer, that we know no stereoisomer. But the product is GLY glycinato is an unsymmetric bidentate ligand, right? So MAB twice is the category. So this can form geometrical isomerism, right? Sorry, geometrical isomerism. Say cis and trans. If this have to show the geometrical isomerism, then it's stereoisomery. Okay, then it's hybridization is actually asked, right? Yeah. So wait, glycinate versus from ligand. And what about the geometrical isomerism in MAB twice? Sorry, optical isomerism in MAB twice. What about the case in MAB twice? This can show geometrical isomerism, right? Sorry, optical isomerism. Since the ligand is actually we can expect the if this is a square planar complex, if MgLy twice is an unsymmetric identity ligand MAB2, if this is a square planar complex, we can expect two geometrical isomer. And if this is a tetrahedral complex, we can expect two optical isomers. So here only mentioned the stereoisomers. So there is a chance for sp3 or dsp2. We can't predict whether it is square planar or not. Okay, because it satisfies the both condition. Okay. Next question. Other than excited diffraction, how could be following pair of isomer distinguished to one another? So you want to distinguish this isomer from one another. Fine. So what about the charge of these two entities? Charge of these two entities. The first one, that is actually a chromium complex, right? Chromium complex with the charge of that entity is what? Charge of that entity will be +3 because coordination number of chromium is 6. Okay. The second one, so here will be -3. What about this one? Chromium still +3, -2. This will be +1. This will be -1. So these two entities can be have difference in what? Charges, right? Both have difference in charges. So two species with a difference in charge can be distinguished by measuring their molar conductance. One with a greater charge have greater molar conductance actually. Okay. So choice will be B. Ready? Next question. The acetyl bromide in the complex acetyl bromide, dicarbonyl triethyl phosphine ion, where Fe carbon bond is number of Fe carbon bonds. So listen, here in acetyl, when the acetyl group is your ligand, actually the coordination by means of what? Carbon. By means of carbon actually. Okay. The next, there are actually two carbonyl. And in triphenyl Triethyl triphenylphosphine. There are actually phosphorus have linked. So actually 1, 2, 3 will be the answer. Okay. 3 will be the answer. Ready? The next. For the octahedral complex, Fe3 plus SCN, thiocyanate. Thiocyanate is a very weak ligand, we know. Okay. F minus, Cl minus, SCN minus. We know that. So very weak ligand. This is spectrochemical series. And Cn minus. If the complex of ion using weak ligand and strong ligand, very strong ligand. The difference between spin only magnetic moment. We know Fe3 plus is actually 3d5. And the very same 3d5 with a strong ligand with the SCN, this will be actually in paired form like this. I'm sorry. That's a weak ligand. SCN is a weak ligand. So something unpaired like this. Now pairing. For Cn minus is a strong ligand. So that will be paired. D5 will be paired like this. So only one unpaired electron. Here n equal 5. Here n equal 1. So what is the spin only difference between spin only magnetic moment means root of 5 into 5 plus 2 minus root of 1 into 1 plus 2. So root 35 minus 9. So that's nearly root 26. So approximately the answer is 4. Okay. Next question. That's a table question that you have to match. Double salt. Double salt is potash alum here. So one is E. So there is only one choice. Zesse salt. That's an organometallic compound we know. Neutral molecule. Neutral molecule. This complex is a neutral one. EDTA. EDTA is a hexadentate ligand. NaCO 4 times. NaCO 4 times is actually paramagnetic, right? Chromium NS3 6 times 3 plus. So it's a paramagnetic. NaCO 4 times, or there is another choice. One G. NaCO4. Is it paramagnetic or diamagnetic? 4s2 3d8. It's paramagnetic. Glass spin complex. Glass spin complex is actually usually diamagnetic. So 7 is actually G. Ready? Okay. Wait, we'll discuss once again. Double salt FeSO4. Zesse salt organometallic compound. Neutral molecule, this one. So 1 is E, 2 is H, 3 is A. 3 is A. Fine. 3 is A. 4 is B. 5 NiCO4. This NiCO4 is diamagnetic. Nickel in 0 state, 4s2 3d8. Yeah, perfect. That's diamagnetic. I'm sorry. This have an effect of 3d8. 10, fine. That's diamagnetic. Fine. That's correct. 6d. Yeah, this is paramagnetic because chromium plus 3 always 3 unpaired electron. Last spin complex 7F. Last spin complex, the best example for last spin complex is cyanide complex. And the glycine is actually a bidentate ligand, glycinate. Right. Next question.